Mila and State AI Lab Montreal. It will be my pleasure to chair this session 2, track 2, which is a session on optimization. The session will have 2 blocks. Each block will have first an oral of 15 minutes and then multiple spotlights. You can ask questions at the end of the orals, but there will be no question during the spotlight. All right, so our first talk will be about trajectory of alternating direction method of multiplier and adaptive acceleration, and it will be presented by Clarisse Poon.
How come it's not showing? Oh, that's on. Yeah. So thank you for coming. This is joint work with Jingwei Liang. So this talk is about how can we accelerate the convergence of ADMM. And so to start with, let me introduce the optimization problem ADM is designed to solve for. So we're thinking about this constrained optimization problem. We want to minimize functions r plus j, where r and j are proper convex, lowest semi-continuous functions, which may be non-smooth. And we have this constraint, which is a linear constraint. A and b are assumed to be injective linear operators. And we make the basic assumption that the set of minimizers is non-empty. So when one talks about acceleration, a very natural thing to think to is the use of inertia. So on a very high level, if you're given a fixed point sequence, this zk plus 1 equals f of zk, where f is some operator, then one way to try to accelerate this is to apply inertia. So you add ak times zk minus 1. So ak is a positive scalar, and you extrapolate in a direction given by a previous iterate. And the use of inertia is very well studied for descent algorithms such as gradient descent or forward-backward. And in these cases, it's known to accelerate the objective convergence rate from 1 over k to 1 over k squared. But in the case of applying inertia to ADMM, the majority of the existing works actually require some extra assumptions, such as smoothness or uniform convexity. And although there are some works looking at dynamical systems in the most general setting of only convexity, the performance of inertial ADMM for the general setting is a lot less clear. And I will show you examples in this talk where the use of inertia will actually slow down convergence. So with this in mind, the contributions of our paper are threefold. First, we studied the local trajectory of a sequence generated by ADMM under an additional assumption of partial smoothness. Then, based on our trajectory analysis, we gave you some insight as to when the use of inertia will accelerate and when it will fail to accelerate. And finally, we developed an acceleration scheme based on the idea of following a local trajectory. So let me quickly recall the formulation of ADMM. So ADMM is dealing with this augmented Lagrangian term. So it iterates between a minimization step in x, a minimization step in y, and a Lagrange multiply update. So one way to study the properties of these iterates is to look at its associated fixed point sequence. So if you define zk equals psi minus 1 plus gamma a of xk, then it's very well known due to the equivalence between ADMM and Douglas-Rashford that this zk satisfies some fixed point equation. And one can equivalently formulate ADMM with the zk as this 4-point formulation. So what we do first is to analyze the behavior of this sequence zk. So I mentioned earlier that we need an additional assumption, and that the assumption is partial smoothness, which is an idea introduced by Adrian Lewis around the mid-2000s for studying non-smooth optimization. So the definition that R is a partly smooth function at the point x relative to a manifold M if its subdifferential is non-empty. And we have got 3 properties. The first is that if you move along the manifold, you are C2 smooth. If you move in the direction orthogonal to the manifold, then you change sharply. So in particular, the tangent space is perpendicular to the space parallel to the subdifferential. And finally, the subdifferential as a set-valued function is continuous all along the manifold. So it turns out that a lot of the non-smooth functions that we often come across are partly smooth functions. So one example is L1, which is partly smooth at the point x relative to the set of vectors with the same support as x. And another example is nuclear norm, which is partly smooth at the point x relative to a set of matrices with the same rank as x. And the key property that we use about partial smoothness here is the idea of manifold identification and local linearization. So this is a result shown in previous work by Lang and co-authors. And what they showed is that if R and J are partly smooth functions around the solutions x star and y star relative to some manifolds, then under some non-degeneracy conditions, after a finite number of iterations, all your iterates will lie on the solution manifolds, so they've got the same structure. And the sequence ZK satisfies this linearization property. So we have a linearization with respect to some matrix M up to small o terms. So what this means for us is that actually the behavior of ZK is eventually very regular. In particular, this behavior will be driven by the properties of this matrix M, and i.e. its eigenvalues. So we looked at two cases to illustrate this idea in our paper. So now I define Vk to be Zk minus 1, and theta k be the angle between two consecutive directions. So the first case is the case of where R and J are locally polyhedral functions around the solutions. So we've got two non-smooth terms. And here you can show that the matrix M has complex eigenvalues, and that the angle will converge to a non-zero value. And what this means is that your iterates will eventually move along a logarithmic spiral. And in the case where you have one smooth term, so in particular where R is C2 smooth around the solution, and A is an invertible square matrix, then you can show that the linearization matrix M has all real eigenvalues, and actually the angle theta k will converge to 0. And what this means is that you will eventually move along a straight line trajectory. And this is provided that the parameter gamma is sufficiently large. So what does this mean for inertia? Well, intuitively, when you apply inertia, you are extrapolating along the direction of travel. And so inertia should work very well if Zk is moving along a straight line path to its fixed point. But as I showed on the previous slide, this is not always the case with ADMM. So coming back to the case of two non-smooth terms, a very simple example is to try to find the intersection of two lines. We're in dimension 2 now. And here the non-smooth functions are simply indicator functions on these two sets. So in this case, the Zk will converge to the intersection point. So on the left here, these dots show you the iterates generated by ADMM. So you move along the spiral. And on the right is this convergence plot with a residue. And you see that as you extrapolate in the direction of travel, you will actually move further away from solution and therefore slow down. The case of lasso is more delicate. So as I mentioned, you have a straight line trajectory only when gamma is above a certain threshold. In this case, inertia does accelerate. But when it is below this threshold, actually inertia can slow down convergence. So we want a scheme which somehow adapts to this local trajectory. And the idea is very simple. So given q plus 2 pass points, we can define our direction vectors and simply fit our coefficients. So fit the past q directions to the latest direction. So you compute these coefficients. Using these coefficients, you can compute a new extrapolation direction and extrapolate. And you can repeat this as many times as you like and hopefully get to the fixed point. So if you carry out this, this very simple framework, then you can write the extrapolation this way. It is simply a linear combination of past directions, where the coefficients is the first column of this sum of matrix powers. So you see that this guy here makes sense, provided that its spectral radius is strictly smaller than 1 for arbitrary s. So this is the proposed algorithm. We do ADMM for q plus 2 iterations and store the past direction vectors. Oops. And then on the q plus second iteration, if the spectral radius of our coefficients matrix is smaller than 1, we extrapolate, otherwise we do nothing. So a few comments is that by choosing this scalar ak appropriately, we can treat this as a perturbation of a fixed point sequence, and we have global convergence. Local convergence depends on how well you fit the coefficients. And we also have some guarantees for this when R and J are polyhedral functions. And the last comment about implementation is that in practice, we could take the number of coefficients to be very small. So in all examples, we took Q equals 4 here. So the extra memory and computational cost is really negligible. So let me end with some numerical examples. So the first are basis pursuit type examples. So we minimize some regularizers subject to affine constraint. The graphs are similar, so let's look at the first one. The angle converges to something which is non-zero. And so here, because we've got two polyhedral terms, we move along a spiral, inertia will slow down, but our scheme gives significant acceleration. So red and black are our scheme for different choices of extrapolation step S. This is the case of lasso. So in this case, we actually have a straight line trajectory, so inertia speeds up. But our scheme can still provide significant acceleration on top of this. And this last example is total variation based in painting. And in this case, both functions are polyhedral, and again, you've got a spiral trajectory. So you see this pink line is inertial ADMM, it slows down, whereas our scheme does provide substantial acceleration. And this last slide is just a visualization of the outputs after 30 iterations. So this is ADMM, this is inertial ADMM, and the bottom two are our scheme. So to conclude, we studied the trajectory of ADMM, and we highlight two cases, the polyhedral case where you will move along a spiral, and the case where one term is smooth where you will move along a straight line. Based on this, we show that indeed, because of the trajectory behavior, inertia can lead to a slowdown. And we give an acceleration scheme based on the idea of following a trajectory. So poster number 115. Thank you.
So we have plenty of time for questions. So there are mics on your left and on your right over there. So if you have a question, please walk up to the mic. Damien.
Hi. Yeah. Hi, Simon. So I have a question. What's the difference between your algorithm and Anderson acceleration?
So I didn't have time to mention this, but essentially our scheme can be seen as Anderson's acceleration applied to the points but shift up by 1. So indeed, it can actually be seen as another form of these vector extrapolation techniques. But I think our scheme also gives a different kind of derivation of these schemes. So there's a detailed discussion of this in our paper.
OK, but it will give you the same coefficient Anderson acceleration in your case, right?
Sorry?
It will give the same coefficient as Anderson acceleration in your case, right? So
yes,
if I apply your scheme and Anderson acceleration...
It gives the same coefficients, but so in Anderson acceleration, you apply it to a set of vectors, right? Mm-hmm. And we apply it to this, it's the same coefficients, but the set of vectors is slightly different. So it is basically just another form of vector extrapolation, and indeed you can just simply see it as basically Anderson acceleration. So the guarantees are the same. It's just that I think our scheme gives a different interpretation of how to derive this, in particular because you can apply it for s less than infinity. So s equals infinity would be Anderson. S small than infinity you can see as a kind of interpolation.
Yeah, but the version of Anderson with has more memory. But we can take it offline. OK, thank you.
Thank you.
Hi, very nice work. I was curious about the connections with recent work on understanding the acceleration of ADMM in the continuous time, which I think had shown that you can get the 1/t² acceleration. So your analysis is for the discrete case, and I think showing 1/k² was open. So I was curious as to whether you could comment on whether you have any rates of convergence, and how do they depend on the smoothness or not of the objective?
So the first comment is that our work, we only give local rates after magnified mode identification happens, so we don't have a 1/k² rate. But the second comment is that these dynamical systems work I think you're referring to, actually, there you're proving convergence rates on the objective. But somehow for some of the problems we look at, the objective is somehow meaningless. If you think of, for example, the intersection of two lines, it's always 0. So we need to study something else other than simply objective. And actually, I think also in this work by René Vidal, So there you have some assumption. So 0 is in the interior of the subdifferential of the one non-smooth term plus A times the other subdifferential of the other one. So this is also not true in the feasibility case problem. So I think somehow the settings in these two works, in their work and our work, is a little bit different. But for sure, I think there's a lot of interesting work to do in the continuous setting.
Thank you.
All right, that was René Vidal for the record. All right, let's thank the speaker again. So we now have 5 spotlights, and the first spotlight will now present.
Good afternoon, everyone. It is my great pleasure to present our work on a symmetrical valley beyond sharp and flat local minimum. This is joint work with Haowei He and Yang Yuan, and I'm Gao Huang. We all come from Tsinghua University. So there's a popular belief in deep learning that flat minimum seems to generalize better than a sharp one. So intuitive explanation is that when the solution is located in a flat region, it is more stable when the test loss, shown by the dashed curve here, is shifted away from the trailing loss, which is shown by the solid curve. Although this explanation sounds reasonable, it may not generalize to high-dimensional space. For example, there's a later paper shows that a flat minimum and a sharp minimum can convert to each other through a simple reparameterization process. And later, another paper shows that for modern neural networks, the minimum seems to be connected. In other words, a sharp minimum and a so-called flat minimum can be located in the same region. So in this paper, we argue that characterizing minimum by flatness or sharpness might be an oversimplification, and we hypothesize that in a local region, the landscape the local curvature might be sharp along some directions, but flat along other directions. So we can formally define this as a symmetrical valley, which is shown by a plot here. So the loss grows smoothly along one direction, but grows abruptly along the other direction. So the asymmetrical valley is not imaginary, but widely exists. For example, we have tested many modern neural networks, like ResNet and DenseNet, on multiple data sets. And on all these cases, we can always find such an asymmetrical direction. So with this observation, we can have some interesting conclusions on generalization. So let's consider 3 cases for the optimization solution. The first case is the solution is the empirical minimizer, which has the lowest training loss. So if the test loss is shifted to the left, in this case, we'll have a relatively low tester loss. However, if it is shifted to the right, we'll have a higher test loss. So in expectation, the loss will be relatively high. Now let's consider the second case. What if the solution is biased towards the flat side? Then no matter the test loss is shifted to the left or is shifted to the right, the expected loss are both relatively low. So for the third case is the solution is biased towards the flat side. Then if the test loss is shifted to the left, then it is OK. However, if it is shifted to the right, then we'll have a much higher test loss. So put the 3 cases together, we will see that the second case is the best, because the solution, when it's located is biased towards the flat side, then it is more stable than the other 2 cases. So we can formally prove this as a theorem. So this is our first theoretical result in this paper. We can show a biased solution generalizes the best. So this theorem has 2 interesting implications. First is converging to which local minimum may not be critical. However, it matters where the solution locates in a local region. And the second implication is that the solution with lowest generalization error is not necessarily the minimizer of the training loss, even with different regularization terms. So an immediate question is, how can we find such a biased solution practically to achieve better generalization? So that's our second main theorem. We can show that there exists a simple algorithm that we simply take the average of the SGD iterations along one optimization trajectory. We can get such a biased solution. So that's our second result. So by experiments, we can show that by taking the average of SGD iterations, we can indeed find a higher training loss but lower test loss. So this phenomenon cannot be well explained by existing theory, but can be well understood in our asymmetrical case. So finally, we want to point out that there are many interesting future directions may follow from this work. For example, how can we develop new algorithms or theory based on this observation? And secondly, our understanding on the asymmetrical value is still preliminary. For example, where the asymmetrical values come from, what network architecture or loss function needed to such asymmetrical values. So if you are interested in any of these questions, welcome to our poster at 116. Thank you very much.
All right, good afternoon, everyone. I'm going to talk about our project on implicit gradient transport, which is a method for stochastic online optimization. So what's the problem we're trying to solve? We're interested in online stochastic optimization where we have a set of parameters theta that we update with a stochastic estimate of the gradient gt. It is well known that gradient methods and accelerated methods do not converge due to the stochasticity in the gradient. Instead, they converge to a region around the local minima and keep bouncing around. Previous work has attempted to solve this problem of stochasticity in the gradient, but either they make unreasonable assumptions, like finiteness of the data set, or they require a lot of parameters to tune. This can be either in the form of having too many parameters, 3 or more, or a specific parameter schedule, like on the learning rate. The question we ask ourselves is, can we design a simple method that converges for this setting? And the answer is yes. The big idea is that we want to transport the gradient information from one iterate to the next one. We do so by taking the gradient estimation at parameters theta t minus 1 and combining it with the stochastic gradient computed at a shifted parameter theta t plus something. This shift has to be carefully chosen so that we can actually reduce the variance at parameter theta t. Once we have this gradient estimate, this variance-reduced gradient estimate, we can easily plug it into any gradient-based optimizer, such as SGD, Heavy Ball, or Adam. Also, our method is simple to implement, as demonstrated by those 3 little equations on the right of the slide. From a theory standpoint, we have 2 results that hold for the restricted case of quadratics with identical Hessians. The first result says that in the presence of noise, the IGT gradient estimator is able to converge at the lower bound rate of 1 over t. Our second result says that in the absence of noise, if you take the IGT gradient and plug it into Heavy Ball, you still have convergence at the accelerated rate. In essence, those 2 results put together provide us with the best of both worlds. From an experiment standpoint, we extensively test our method on supervised learning, meta-learning problems, and reinforcement learning problems. As you can see on the left side of the slides, we tested our method on Cypher10 and ImageNet. Here we see that the IGT-based methods converge much faster than SGD, Heavy Ball, or Adam, due to the reduction in noise. Similar results can be observed for MAML for the meta-learning scenario and reinforce on the LQR setting. To conclude, I would like to thank you for your attention, and please visit come see our poster number 96, not 2887, which is titled Reducing the Variance in Online Optimization by Transporting Past Gradients. I would also like to thank my collaborators, Pierre-Antoine, Reza, Ioannis, and Nicolas. Thank you.
So, hello everyone, I'm Stefano Saramanelli and I'm going to present Who is Afraid of Big Bad Minima. So the question that we want to answer is when does gradient flow dynamics find good minima in high-dimensional non-convex problems, and why? So if you look at this problem from a geometrical perspective, in the literature you will find that many people have shown that all the spurious minima disappear, and so only good minima remains, and so it doesn't really matter where your gradient flow dynamics starts, you will always find a good solution. Now, what we show is that actually you can find situations where gradient flow is working, but exponentially many spurious minima are present. So let me introduce the model that we analyzed, which is the spike matrix tensor model. That is an inference problem where you have a signal, x star. You use it to construct a matrix and a tensor, and you want to minimize the L2 distance between the matrix and the tensor. So now we use the Katz-Rice formula to analyze the geometrical properties of the landscape, and we use Martin-Singer-Rose formalism to characterize the performance of gradient flow. So let's start with the dynamical part. What you obtain is a phase diagram that looks like this. So on the horizontal axis, you have a parameter of the model, and on the vertical axis, you have the signal-to-noise ratio. So what you can see is that there is this blue line that you can identify analytically, and above which gradient flow starts to find good minimum, and below which gradient flows find only non-informative minima. So this is not very surprising. If the signal-to-noise ratio is strong enough, gradient flow is working. What is interesting actually is when you put also the line on the geometrical, on the geometry. So if you consider the transition above which all the spurious minima disappear, you will find that this line, the dotted purple line, is above the blue line that we've found before. So this means that you have this gray region where gradient flow is finding a good solution, but exponentially many spurious minima are present. So what follows is understanding why this is happening. And so if you take a cut on this phase diagram, and you look at the minimum, and the good one is the blue one, you will find that observing only the minima will not help you in understanding when gradient flow is working, which is the blue line. What you need to do is to go further and to study also the saddles. And you have to understand that not all the minima behaves in the same way, and some of them are more relevant than others. And the more relevant ones are depicted here. And basically, you will see that if you analyze them in the signal-to-noise, as the signal-to-noise ratio increases, at a certain point, they will develop an instability, and they will become saddles of order 1. This negative direction is pointing toward the signal. So what is happening is that in this region, basically, your dynamics starts at random in the landscape and is still attracted by the one that used to be dominating minima. But now what happens is that gradient flow will identify the negative direction and will be redirect on the good minima. This is a cartoonish representation, but all the analysis that is done here is quantitatively, and so you can actually draw these curves in a rigorous way. So if you want to know more about the work, future direction, and where you can apply this kind of analysis, please come to my poster 127 this afternoon. Okay.
Hello, my name is Fabian, and this is joint work with my colleagues Armin and Volkan in EPFL, Switzerland. So many years ago, there was this problem where given noisy measurement of some signal, people wanted to recover the original signal given these noisy measurements. And people didn't know how to do that, but around 2006, Donohoe, Candes, Tao, and Romberg came and said, like, okay, we're going to assume that the signal has some sparse representation in some basis. And then with some convex programming, we can do the trick and we can reconstruct our signal. This is what is now known as compressive sensing. So around 2017, Bora, Jalal, Price, and Alex Dimakis came with this idea, okay, why we have this generative adversarial network since 2014 or maybe even before that. So why don't we just replace this sparsity prior with a prior that our signal has to lie in the range of a generative network. Now the problem is non-convex, but it looks like in practice gradient descent methods work. So we thought, okay, let's try to come up with some ADMM type method to solve a more general class of optimization problems that arise in this setting, but which is not limited to these compressive sensing scenarios. So we study the following optimization template, where L is some convex smooth function, R and H are convex, non-smooth, but with efficient proximal mappings, and G is our generative model, which we assume to be smooth. So here's the variable C is the noise vector that you input to the generative network. So you want your W to be G of C for some C. So we introduced the well-known augmented Lagrangian function, which has some square penalty on this norm, which is we call the invisibility. And we recast our problem as a min-max optimization problem. And so we propose the following updates. First, for some step size beta, a proximal gradient descent update on the variable C. For W, also for step size alpha, we do one proximal gradient descent update on the variable W. And finally, a gradient descent update on the dual variable lambda with some sequence of step sizes. So recall that the classical ADMM correspond to the exact minimization on the variables C and W, but given the non-convexity introduced by the generative network, then this is not possible in general. So this is why we studied this modified version that requires only access to first-order oracles for the generative network G and the loss L. So when would you expect like good performance of these type of algorithms? So one simple example is to study these problems. So suppose you want to find the closest point in the image of a generative network to a given reference point W natural, where the distance is measured in L infinity norm. So your optimization problem would look like this, and you could cast it in this form. So this is motivated by a denoising preprocessing step that has been shown to improve the robustness of deep learning classifiers. So in this case, if you use a subgradient method, you will see that your gradient is really sparse. It only has one component which is non-zero, and this really, in the left plot, we see that this really degrades the performance of gradient descent type methods like ADAM or just plain gradient descent. Whether method can efficiently reduce the loss. And on the right hand, we compare the baseline of projecting in L2 norm compared to this L infinity norm minimization, and we see that we can get some better robustness in practice with the same amount of computation or less than gradient descent and L2 minimization. So for more details and questions, please visit us in poster 76. Thanks.
So hi all, my name is Aaron Sidford. Today I'm going to be telling you about the complexity of highly parallel non-smooth convex optimization. This is joint work with a number of fantastic colleagues I've had the great pleasure of working with over the last year, namely Sebastian Bubeck, Qizhe Jin, Yintat Li, and Yuanji Li. So as the title of this talk suggests, the problem that motivates our work is that of non-smooth convex optimization. So in this problem, we have a d-dimensional convex non-smooth function f that we assume is 1 Lipschitz and attains its minimum at a point of L2 norm and most 1. Further, we assume we can access this function f through a first-order oracle, which when queried at any point x, outputs the value of the function and the gradient of the function at this point x.
Now, in this problem, the question we ask is how many queries do you need in order to compute an epsilon optimal point, meaning a point who has value at most epsilon more than that of the minimizer. Now, this is an incredibly fundamental, very well-studied problem, and the algorithms for solving this problem form the basis of our optimization and learning theory toolkit. So on the one hand, you could use gradient descent to solve the problem in 1 over epsilon squared iteration, or 1 over epsilon squared queries. And on the other hand, you can use the center of gravity method to compute an epsilon optimal point in d log 1 over epsilon queries. Now, given the pervasive and fundamental nature of this problem, you might try to improve the complexity of these methods, but unfortunately, this is impossible in the worst case. So if you do at most d queries, the accuracy achieved by gradient descent is optimal up to constants, and when you do more queries than that, the accuracy achieved by cutting plane methods are optimal up to a constant. Given that, the question we asked in this work is, what if you still want to solve these problems and you have an abundance of computational resources and you can compute the value of the function and the gradient of the function at many points at the same time? In this context, is it possible to get improved parallel algorithms for solving the problem? Now, like many fundamental optimization problems that I'm excited to work on, it turns out that Nemirovsky did a lot of heavy lifting for me many years ago. And for this problem, he introduced a natural parallel version of the problem, where instead of having a first-order oracle, you assume you have a parallel first-order oracle. This is an oracle that you can query at some k points at the same time and get the value of the function and the gradient of the function at these k points simultaneously. Given such a parallel oracle, you can measure the complexity of a corresponding parallel algorithm in terms of its depth, the total number of queries you need to make to the oracle, and its work, the total number of points whose function and gradient is evaluated at the end. Now, the question we asked in our work is if you're in a highly parallel setting where you're allowed to pick k to be polynomial dimension, so you can make a polynomial number of queries every round, what is the best possible depth you can achieve? Now, the results I've already told you can be easily cast in this framework, so gradient descent and cutting plane methods are highly parallel algorithms of depth 1 over epsilon squared and d log 1 over epsilon correspondingly. And you might ask, in this setting, can you get better depth? Now, interestingly, there was this beautiful result of Ducci, Bartlett, and Wainwright that showed, in fact, you can do better in some cases, and they gave an algorithm with depth d to the 1/4 over epsilon. This is better than these two methods when you consider algorithms that are going to have depth between root d and d. Now, you might try to improve this even further, but there was this result of Nemirovsky that was rediscovered by Belansky and Siger that showed up to depth d to the 1/3, the accuracy achieved by gradient descent is the best possible. So prior to the work, this was the state of the art for solving this problem. Up to depth d to the 1/3, gradient descent was known to be optimal. At depth root d, there was then a better stochastic algorithm, and that was better than cutting plane methods up to epsilon being 1 over d to the 3/4. So the two main contributions of our work are as follows. On the one hand, we showed you can improve the lower bound to root d. So you can show that gradient descent is the best possible up to depth root d, thereby fully characterizing when gradient descent has optimal depth. And on the other hand, when gradient descent is no longer the best possible, we showed that there's a better algorithm with improved depth. Namely, we gave an algorithm with depth d to the 1/3 over epsilon to the 2/3. Whenever the previous work of Ducci, Bartlett, and Wainwright was faster, this gets an improved runtime. And interestingly, it has improves on cutting plane methods all the way up to accuracy 1 over d rather than 1 over d to the 3/4. So those are the main two contributions of our work. We now understand that gradient methods are optimal up to depth root d. In the case that they're no longer optimal, we have these improved accelerated stochastic methods. Now, if I had more time, I'd tell you more about the techniques that underlie this work. I think they're interesting in and of their own right and of possible further utility. However, I don't think I can do that in the next 10 seconds. So if you'd like any further information about how to use certain shielding or wall building techniques to improve the previous lower bounds, and you want to use high order acceleration or generalizations of that to improve, come to the poster. Thanks.
All right, so this concludes our first block of spotlights. So we will now have an oral, 15 minutes. You can ask questions at the end. And the talk will be on necessary and sufficient geometries for gradient methods. And it will be given by Daniel Levy.
Just give me 1 second. OK, that was something. So hello, everyone. I'm Daniel Levy, and today I'll be presenting necessary and sufficient geometries for gradient method. This is joint work between me and my advisor, John Ducci at Stanford. So the problem we care about is the problem of stochastic convex optimization. So the goal is to minimize the function little f within a certain constraint set. And the particularity of it is that the function can be written as an expectation of a function big F under a certain distribution P. And what we get to observe is a few samples from P. And this is essentially the fundamental problem of machine learning and statistics. If you think of P as the data distribution, x1, xn as the training data, F as a convex loss function, and big theta as the model family. And the most popular way, and our favorite way to solve it, is the stochastic gradient method, or SGD, but also its many variants, like mirror descent, dual averaging, and other adaptive methods such as AdaGrad. But an important question that remains is how do we understand optimality in stochastic optimization? And more precisely, when are each of these methods optimal depending on the geometry of the problem? And this is actually quite an important question because depending on the geometry of the constraint and the geometry of the features, these methods can converge at very different rates. So let's try to paint a stylized picture of domain that people like to tackle in practice. So in vision, features are often bounded in L2 norm, and we wish for a classifier that is also bounded in L2 norm. And the rate that SGD get is 1 over square root n, where n is the number of sample. And that's actually very good news because that's also the best rate. But now if we turn to a slightly different domain, genomics, we now have dense features because it's plus or minus 1, depending on whether or not a mutation is present. And we wish for a sparse classifier that only selects a subset of relevant features. And the rate that SGD gets is now square root d over n, where d is the dimensionality of the features. But this is not optimal anymore because mirror descent with the right regularization can get square root log d over n. So we can get a logarithmic improvement by choosing a slightly different method. And similarly, if we think about NLP, the features are usually sparse. So if you think about bag of words. And we wish for a dense classifier. In other words, one weight for every word. And again, SG gets the rate square root d over n, when adaptive methods such as AdaGrad can get 1 over square root n. And these gaps can get quite large in practice. And the interesting thing is that for all of these methods, essentially iterate the same identity for different regularizer h. And dh in this case is a Bregman divergence that measures the distance between points according to h, the regularizer. So the challenge of choosing the right method actually reduces to the challenge of choosing the right regularizer. And how do we actually choose this regularizer? So to do this, we're going to look at a classical model of statistics, which is the Gaussian sequence model. So in the Gaussian sequence model, we get to observe a single sample y of a vector theta corrupted by noise. And the goal is to estimate theta within a certain constraint set big theta. So immediately, a few estimators come to mind. So a natural one would be the maximum likelihood estimate, so just returning theta hat of y equals y. If we're trying to be a little bit more fancy, we can do theta hat of y equals ay, so a linear estimator, or more generally, any measurable function of y. And the important part is that all of these estimators are essentially maximizing a regularized log likelihood. And if we do a little bit of rewriting, it can be rewritten as a linear term of y plus a regularizer r. So we're now minimizing a linear term of y plus r. And depending on how we choose r, we will get very different estimators. So if we choose r to be the half square norm, we get the MLE again. If we choose r to be a quadratic, we get the linear estimator. And if we choose r to be arbitrary, we get the general estimator. And there is a very important result from Donoho and co-authors in the 1990s that state that if your constraints are quadratically convex, which is a term I will define in a minute, then a linear estimator is minimax optimal. And they also prove a converse, which says that you can exhibit non-quadratically convex set for which the optimal estimator needs to be nonlinear. And just to define it, a quadratically convex set is one such that when you square its element, meaning you take the component-wise square of each element in the set, you remain convex. So if you think about the L1 ball, if you square it, you get the L half ball, which is clearly not convex. If you take the L2 ball and you square it, you get the L1 ball, which is convex. And essentially, all balls for p greater than 2 are quadratically convex, and all balls for p less than 2 are not quadratically convex. And the way to think about it is that a quadratically convex set is kind of full. And this is actually a very historically important result because it's the first time that on such a simple problem, someone exhibited the need for nonlinear methods. And it turns out it's modernly important as well because a lot of problems in high-dimensional statistics, such as non-parametric regression or density estimation, actually reduce to the Gaussian sequence model. And now, thanks to our work, the Gaussian sequence model also illuminates stochastic optimization. OK, so now let's turn to the problem at hand, which is stochastic optimization. So the generic form of this algorithm is to first choose a strongly convex regularizer H with respect to a certain norm, and a step size alpha. And then each of these essentially minimize a regularized linear model around the current estimate. And if we choose H to be, again, the half-square norm, we get back the well-known SGD. If we choose H to be a quadratic, we get back preconditioned SGD. So you actually multiply your subgradient by a linear matrix before doing your update. And if we take H to be arbitrary, then we get the general form of mirror descent. And the conjecture is essentially the parallel to the one in the Gaussian sequence model, but now for stochastic optimization. So when the constraints are quadratically convex, then linear updates are optimal. And conversely, non-quadratically convex set can require nonlinear updates. And this work is just proving the conjecture and showing that the analogy holds completely. OK, so now let's make things a little bit more precise and say what we mean by optimality. So first of all, we consider big F a convex loss function and P a distribution over X. And we measure the quality of an estimator or an algorithm by its risk, meaning the difference in error value, in function value between the points it returns and the optimal points. And for mirror descent, we have this well-known risk bound that says that the risk is less than the size of the domain measured by H, plus the size of the subgradient measured in a dual norm. And now if we want to characterize the complexity of a class of problem, we need to think not about one function, but about a collection of functions and a collection of distribution. And the minimax risk is going to be the minimax risk is going to be the risk of the best estimator on the worst function and the worst distribution. And the family of functions we're going to consider in this work are going to be the function. So we first choose gamma, a norm, so gamma as gradient, it's mnemonic, and R a radius. And the family of functions we consider are the functions that are subgradient bounded in gamma norm by R. And essentially, the relationship between the geometry of gamma and the geometry of the constraint is going to govern the minimax risk exactly. So now let's turn to proving the conjecture. So we have to distinguish between, so we first choose a quadratically convex constraint set, and we now have to distinguish between geometries of the gradients. So if the gamma ball is quadratically convex, then we can compute the minimax risk, and it's simply the size of the set measured in the dual norm divided by square root n. And the very interesting thing is that just a diagonal rescaling of SGD is minimax rate optimal. Now, if gamma ball is a weighted LR ball, which is now not quadratically convex because R is less than 2, we can also compute the minimax rate. That looks a little bit different. And the diagonally scaled SGD is still rate optimal. And if it's neither of these, which would be quite pathological, we still have some results, but it's a bit less precise. And the takeaway from this is that essentially, if your constraints are quadratically convex, then simply doing diagonal rescaling should be rate optimal. And that's a setting where you should turn to methods like Adagrad that builds actually a diagonal preconditioner for your problem. OK, so now we can switch gears and move to the converse. So can we show that for QC constraints, linear methods are going to be optimal. What about now for non-QC constraints? So are linear methods enough to achieve optimality? And in general, they are not. And to exhibit that, we're going to just consider very simple non-quadratically convex sets, which are going to be the LP ball for P between 1 and 2. And we're going to measure the gradients in the dual norm. So the strategy is to show that first nonlinear methods are optimal, and then construct very hard problem for preconditioned gradient descent. And what we're going to do, which is interesting, is that we're actually going to evaluate the gap on specific problems instead of comparing upper bounds, which is not correct. OK, so the first theorem is that we can actually compute, as we said, the nonlinear mirror descent is going to be minimax optimal in this class of problem. And we can actually compute the optimal rate. And now let's turn to constructing hard problem for precondition SGD. So we actually construct this problem in the online learning setup because it's for clarity. So we first choose a preconditioner A, and we choose a P between 1 and 2. And then we're just going to exhibit a sequence of function that achieves high regret. And the way we do it is that the average regret is going to be essentially the size of the set measured in a primal norm times the size of the subgradient measured in a dual norm divided by square root n. And essentially, we're going to play gradients that are going to maximize either of these terms, but by playing them in the right proportion, we can achieve very high regret. OK, so these theorems actually characterize the gap. So if P is 1, meaning that the set is not quadratically convex at all, then the average regret of linear methods is greater than square root d over n. But the average regret of nonlinear function is less than square root log d over n. So the gap is characterized exactly, and it's square root d over log d. Now, if p is very close to 2, meaning it's almost quadratically convex, then the gap is essentially a constant factor. So the takeaway from this is that if your constraints are not quadratically convex, then linear type methods can be arbitrarily suboptimal in high dimension. So it might be best not to turn to them in that setting. OK, so to conclude, in this work, we exhibited an analogy between the Gaussian sequence model and stochastic optimization, and we show how results in the Gaussian sequence model can actually translate into results in stochastic optimization. We provided recommendation on which algorithm to use depending on your geometry. So if your constraints are quadratically convex, Adagrad seems like a good bet. If they're not, then maybe not Adagrad, maybe nonlinear mirror descent or something else. But there are still a few open questions. So we know that for hyperrectangles constraint, Adagrad achieves the optimal rate. For arbitrary QC sets, it's not clear that it does. I suspect it does, but it's still an open question. Adaptivity is also an important thing to figure out because we usually don't know the geometry in advance, and it would be nice to just have methods that work on the get-go. And the final thing is actually wondering if minimax is the right notion of optimality, given that it can be pretty conservative and doesn't actually reflect what practitioners face, where they're handed a single function and a single distribution. So you can find our paper online and come to our poster, number 111, in East Exhibition Hall B+C.
So we have some time for some questions. So there are a mic to your left and to your right. Please walk up to the mic to ask a question.
Sorry.
If there is no question, I can ask a question. So, do you have other practical guidance that could be provided from this work for people?
So I think you mean other than the constraints?
Yeah.
I think that's already a pretty big one because in practice, people kind of know what classifier they want. So already, you might not know the data you have, so the geometry of the gradients, but you will always know what classifier you want. And in that sense, this work already provides you which method to use. Because if you, yeah.
Any other question? All right, so if not, let's thank the speaker again and have the first spotlight presenter. All right, so now we have a block of 5 spotlights. No question to be asked, but pay attention. All right, and the first talk will be given by Celestine.
Thank you. Hi, everyone. My name is Celestine, and this is joint work with my collaborators, Nicolas Ioannou and Thomas Pernal from IBM Research. In this talk, I will focus on a different aspect of machine learning training. So I will talk about how knowledge about system characteristics can be incorporated into the algorithm design to improve performance. And we study this at the example of the coordinate descent algorithm. This is a very popular method for training generalized linear models. It's conceptually simple, so in each iteration, you randomly select a coordinate and you compute an update along that coordinate direction. So in this original form, this algorithm is highly sequential. So it's not well suited to take advantage of parallel hardware architectures. And people have realized that, and they have developed parallel versions of this method. So the core idea is that you update multiple coordinates in parallel across different cores. And this is a first step towards system awareness. So people have taken this multi-core parallelism into account. But what we argue in our paper is that this is not the end of the story. So modern CPU is not just a uniform collection of cores. It's much more than that. And there are a lot of other structural constraints and bottlenecks that one could take into account to improve performance. And in our paper, we have identified 3 such bottlenecks, while in this talk, I will just focus on one, which is a memory contention issue. So if you look at the coordinate descent algorithm, there is an efficient implementation of coordinate descent is always involving some auxiliary information that you keep in memory. This is denoted by V in this algorithm. So the challenge is now that if you parallelize updates, you can parallelize model updates across cores, but multiple cores will access the same memory location of this shared vector and write to it. So this can cause contention issues and lead to massive delays, which can really degrade performance of your algorithm. So we want to avoid such situations as good as possible. I think a straightforward approach to do that is to just replicate the shared vector. So each core has its own shared vector to work on. If we look at that in our algorithm, this means that instead of having one vector v, we have multiple ones. So each core works on a separate vector, which is synchronized periodically. For those of you that are familiar with the literature on distributed learning, this is very similar to, for example, distributed methods such as COCOA. But this is really nice, so because this allows us to transfer ideas from distributed learning to this parallel setting. We can, for example, reuse their formulation of the auxiliary model to inherit very strong convergence guarantees. So this is, in the otherwise not so stable and scalable asynchronous method, we have now a method which has nice guarantees. And you may now ask, why have people not done that before? And I think the reason is that distributed methods, in general, converge very slowly. So they are not really suited to achieve acceleration through parallelism. They are designed to work on large data sets. So to illustrate this, in a distributed method, the data matrix is partitioned across physical workers. So each node has only a view, only sees the local data. And to achieve global convergence, they introduce this shared vector. So the main motivation here is communication efficiency. So to have data locality to achieve communication efficiency, because that determines performance of distributed methods. But we are now in a different setting. We have now a shared memory machine, so we don't really care about communication efficiency. So we can do things that we could not do previously. And one of these things is, for example, to repartition data. So in each iteration, we can use a different partitioning. And we found that this is very effective and can alleviate a lot of the convergence slowdowns of distributed methods. So this combination of this replicated shared vector together with the partitioning is a very efficient way to address this contention issue on the shared vector. And this is only one of the 3 bottlenecks that we've addressed in our work. If you want to learn more about the others, please drop by our poster. And yeah, one thing that I feel is remarkable is that these methods have been studied for quite a long time. And now by taking a bit this different perspective on the methods, we can boost performance by another order of magnitude. Yeah, our poster is 39. See you there.
All right, so thank you very much for coming to my presentation. I'm Ying Xiang, and these here are my collaborators. Hao Xiang is a first-year PhD at UIUC. The other two are my advisors, Niao and Nigar. So the motivation of this work is to learn positive valued functions which appear in many places in machine learning. For example, learning probability density functions or intensity-related functions for point processes, etc. And the learning of those functions can be posed as a pretty general constraint optimization problem, where you minimize a loss objective f over a Hilbert space H. And here, H bracket plus is just a notation called positivity constraint that just says x, your estimate has to be pointwise positive over its support. So previously for this problem, there has been several regimes handling this constraint. For example, when f is convex, you can just apply projected gradient descent in reproducing current Hilbert spaces. And this approach is theoretically guaranteed, but computationally it can be expensive on large data sets because every iteration you are just doing this large-scale quadratic or semi-definite programming for your projectional operation. Another approach is the link function approach, which says instead of estimating x directly, you go and estimate y. You go and assume x equals y squared and estimate y instead. So this effectively removes the positivity constraint, so it's computationally more efficient. But at the same time, it compromises theoretical guarantees because typically you are now left with a non-convex optimization problem. So our goal of this work is to see whether we can obtain both theoretical guarantees and computational efficiency at the same time. And the idea is very simple. Just start using the mirror descent algorithm to guarantee positivity. So this is a classic mirror descent iterate where delta phi is your Bregman divergence, so nothing new here. The idea is that if you choose a proper Bregman divergence, then you will get a positivity preserving update. For example, if you use the KL divergence here, you will get this multiplicative update rule where every iteration you multiplies over your previous update an exponential term. So the idea is that if you initialize to be positive, then you do not have to worry about this positivity constraint throughout the entire procedure. But the challenge of this approach is that sometimes you may run into difficulty obtaining or evaluating your gradient. And here's one concrete example of learning a Poisson process. So if you consider the objective 3, which is maximum likelihood estimation objective, average over infinite number of trajectories, and if you take the gradient of that, you get equation 4, which is 1 minus x star over x. So x star is the ground truth you're going to estimate. So if you set your gradient in 4 to be 0, you will find that indeed x star is a minimizer of the problem. But the problem with that is that you actually cannot apply gradient or mirror descent algorithm in practice because you do not know x star. So how can we address this problem? It turns out that the solution is to not use the exact gradient, but just use some direction that's close to it. And here's a brilliant concept originally proposed by Polyak in 1973. It just says you can use something called a pseudo-gradient that's a random direction that on average has an acute angle with the true gradient. And if you use that in your gradient descent algorithm, then you will get all kinds of nice properties in terms of convergence. And what we did in this work is we generalized this concept to the mirror descent algorithm. And when doing so, we found that the Bregman divergence really come into picture. And so what's changed in the definition is now you are left having this weirdly looking thing which we call gradient adapted to Bregman divergence. So now we are ready to introduce the pseudo-mirror descent algorithm, which is just a plug-in type of method. You go and use your classical mirror descent algorithm. And whenever you find yourself in difficult evaluating your gradient, you just plug in a pseudo-gradient instead. And this algorithm is theoretically guaranteed under standard assumptions in terms of convergence of gradient norm as well as objective value if you have smoothness condition on the objective. In practice, you can also efficiently construct pseudo-gradient at the same time. So in the Poisson example, here's one possible pseudo-gradient is the difference between two sets of kernels, where the first set of kernel, the first index is sampled from your estimate, and for the second set of kernel, the first index is summoned from the ground truth. And these are just some curves. I don't think I'll have time to introduce, but I think it just shows our algorithm works and works well in practice. And for more information, please come to poster 55, East Building tonight. Thank you.
Hi, just before the next satellite, I make an announcement. If the authors for the Sinkhorn-Barry Center paper can come in the front. Are you there? Okay, thanks. Perfect.
Hi everyone, I'm Ali, and today I'm going to present you our paper titled UNIXGrad, a universal adaptive algorithm with optimal guarantees for constraint optimization. And this is a joint work with Kifir Levy, Francis Bach, and Volkan Cevher. So I'm sure you've all seen this template before. This is very simple. We just want to minimize a convex function f, which can be smooth or non-smooth. And we want to optimize over a compact and convex set k, which we assume that we can easily project to. In this work, we aim to develop an algorithm which is universal in the sense that it achieves optimal convergence rates for smooth and non-smooth problems simultaneously. And we also want to be adaptive, meaning we want to do so without knowledge of Lipschitz constant and or the variance of the gradients. So to the best of our knowledge, this is actually the first algorithm that achieves so in the constraint setting. So here's our algorithm, which is called UNIXGrad, and it stands for Universal Extra Gradient. And this template is actually known by different names, one of which is extra gradient, another is mirror-prox. So what we do is we are actually proposing three main modifications to the algorithm. First one, we introduce the weights alpha t, which are equal to t. They grow linearly with time t. And second is we define our own adaptive learning rate, which is eta t. In equation 3, you can see that. And it's actually inspired by optimistic mirror descent algorithm. And third one, we redefine gt and mt. So we define gt as the gradient evaluated at x bar t, which is a weighted average of x sequence. And mt is the gradient at z tilde t, which is very similar to x bar t. You just replace xt with yt minus 1. Hence, this gives you the connection to extra gradient algorithm. I'll give you some preliminaries before moving on to the theoretical results. So first, on top, we define a notion of weighted regret, where we take the gradient at x bar t rather than xt itself. And we also weight this inner product with alpha t. So in equation 4, you can see our adaptive regret bound, and this is parallel to optimistic mirror descent algorithm with a little twist by up to introducing alpha t squared weighting factors. And in equation 5, you can see one of our contributions, which is that we propose an online to offline conversion scheme such that you can upper bound the convergence in objective with respect to x bar t with 2 times the weighted regret divided by t squared. So these are actually the basis of our analysis, and we are showing this in our paper. Now the convergence properties. When f is non-smooth and if it's g Lipschitz, we show that the convergence rate is of order g divided by square root of t, which is optimal up to some constant. And one important remark is that the regret analysis is agnostic to the definition of GT and MT. You can take it anything you want. It just needs to be upper bounded by some value. But in order to go from regret to rate, you need to use the specific definitions of GT that we proposed in our algorithm. So when f is L-smooth, meaning it has L-Lipschitz continuous gradient, with deterministic oracles, we achieve acceleration. The rate becomes L over t squared. And when the oracle is stochastic, the rate becomes L over t squared plus sigma over square root of t, where sigma squared is the variance of our gradients. One important remark is that when f is L-smooth, we don't require the gradients to be bounded anymore. So I'll conclude with some basic numerical examples. So here we have least squares with L2 norm ball constraints. And one important thing to note about these graphs is that the convergence behavior of our algorithm for stochastic oracles is much better in the average iterate compared to the last iterate. And this is something that we've observed consistently for different examples, different data, and different initializations. And we also trained an SVM classifier with some adaptive methods, including AdaGrad, AMSGrad, and XLGrad. And we're showing that actually our algorithm proves some comparable performance both in convergence and in test accuracy. So thank you for listening to the talk. You can see our poster at 1:33. Thank you.
So hi everyone, my name is Julia, and I will be talking about synchron barycenters via Frank-Wolf algorithm. So this work is motivated by the fact that averaging or summarizing a set of data is an important task in machine learning. And just to give some context, if you are on RD, the barycenter or average of a set of vectors just corresponds to the arithmetic mean. If you are in more general metric spaces, what we call average or barycenter is the so-called Fréchet mean. And in this work, we want to compute the barycenters of probability measures. So while on the Euclidean setting, the standard distance that you use to compare vectors is the Euclidean norm, on the space of measures, you have several options. You can use Kullback-Leibler, total variation, Ellinger distance. In this work, we adopt an optimal transport perspective, and we want to compute the barycenters with respect to synchron divergence. If you're not familiar with the synchron divergence, you can just think that it's a way to compare probability measures. And the interesting properties are that so synchron divergence has a geometric flavor, so it's coherent with the geometry of the underlying domain. And also, it's well-defined and meaningful on measures with non-overlapping support. So to formally state the problem that we are addressing, given beta 1, beta m probability measures, we want to minimize over the set of probability measures the barycenter functional, which is just given by a convex combination of synchron divergences. Now, in the literature, there are two families of approaches to address this problem. So if you assume a barycenter is given by alpha star, so the weighted combination of Dirac deltas, the fixed support methods aim to fix the support points xi a priori and only optimize on the weights. And in this case, the convergence analysis is well understood, and there are very fast algorithms to compute the barycenters. The second family is given by free support methods. In this case, you want to compute both the weights, AI, and also the support points. And the usual approach is to do an alternating minimization. However, in this case, you have no convergence guarantees. So the goal of our work was to propose a new method with free support, for which we can prove a convergence result and rates. So the algorithm that we propose is based on a Frank-Wolf algorithm, and in practice, it works as follows. The initialization is just given by alpha 0, which is a Dirac centered at some point in the domain. And then for each iteration, you want to compute the gradient of the functional using a synchron algorithm. This gradient happens to be a smooth function on the domain. So step number 2 is to find a minimizer of this function. And then you use this point xk plus 1 to create the new iterate. So the new iterate alpha k plus 1 is just given by a rescaling of the previous iteration and some weight times the Dirac centered at the point that you just found. So just to give an intuition of what happens at, OK, the GIF is not working, sorry. I wanted to show like the rescaling of the weights, but you can come to the poster for a clearer picture. And the algorithm works both for discrete and continuous measures. When you have to deal with the continuous measures, what you do is you take some samples, and then we compute the barycenter using the samples. The key question is to understand at each iteration how far we are from the ideal barycenter. And our convergence analysis answers to this question, and it highlights both the dependence on the number of iterations and the sample complexity of the overall problem. So in particular, if alpha k is the case iterate of our algorithm applied to empirical measures which are obtained with a sample with n points, then in high probability, the barycenter functional at alpha k minus the minimum of the barycenter functionals is upper bounded by some constant over the minimum between k and, which is the iteration, and square root of n, where, again, n is the number of points that you sample from the input. You see that you can play with the trade-off between the rate of convergence that you want to achieve and the number of points that you are allowed to sample. And to wrap up, we proposed a method to compute synchron barycenters with free support, such that it handles both discrete and continuous measures, and for which we are able to show convergence guarantees and rates. For more details and for the experiments, please come to poster 113. Thank you.
Hi, everyone. I'm Hussein, and I'll be talking to you about learning dynamic polynomial proofs. So assume that you have that you're given a multivariate polynomial p that depends on variables x1 to xn, and your task is basically to prove that this polynomial is non-negative on the continuous hypercube 0, 1 to the n. So this is a fundamental computational task and a general problem in the sense that many hard problems can actually be formulated as follows, such as SAT, TSP, stable set, max cut, and so on. And also other problems in control theory and program verification and so on. So our goal here is basically to train an agent using reinforcement learning to prove the non-negativity of polynomials, basically, of multivariate polynomials. So how do we go about solving this problem? So we start basically with the axioms. So the axioms that we have is that x is basically between 0 and 1. So we have all the inequalities that xi is between 0 and 1. And so we're going to derive a lemma from these axioms. And then from the lemmas, we're going to derive other lemmas and so on and so forth, till we get basically to the final result we care about, which is that the polynomial p that we care about is non-negative. So at each step, the lemma that we're going to derive is a new polynomial that is non-negative. And we're going to basically go from a lemma to the next lemma through what we call an inference rule. Okay, so it's something that basically preserves the non-negativity. So for example, the inference rules that we're using is that if you have a polynomial that is non-negative and you multiply it by xi, it's also non-negative. And also if you multiply it by 1 minus xi, it's non-negative. And if you do a non-negative linear combinations of polynomials, it's also non-negative. Okay. So, and then the final thing we care about, basically, which is to prove that p is non-negative, it basically corresponds to a composition of these inference rules that basically yields the polynomial p. Okay. So, so obviously there are many paths that start from the axioms and go to different polynomials. So obviously the hard thing here is basically to find this path starting from the axioms to the polynomial we care about. And this is exactly where we use machine learning. In particular, we use a reinforcement learning framework. The state in our case here is basically made up of two things. The memory, here called M0, which basically contains all the polynomials that have been already proven to be non-negative. Okay, and then P is obviously our target. Okay, so here, for example, our elements in the memory is X, all these things that are in the axioms. So these things are non-negative, and then the action that we're going to take at each step is basically a new polynomial that is basically non-negative. Okay, and it's going to be derived from the elements in the memory by applying one of the inference rules I was just talking about. Okay, so in this case, for example, we're going to take x2 and multiply it by x1, and then we get basically that x1 x2 is non-negative. What we're going to do next is basically to update the state and give some reward, okay? And then we're going to loop over and over again till basically we get more and more polynomials that are non-negative till we get the p we care about eventually. So in practice, what we actually do is that we use a DQN agent, a DQ network agent. And in order to make this work, we actually need to incorporate two important ingredients. So first of all, we need to have dense and unsupervised rewards. So one way of doing things is basically to give a reward at the end, the complete end. If you give a reward of 1, if your agent managed to find a proof, and 0 otherwise. But this doesn't work. So you have to basically give gradual rewards. Yeah, so I'll give more details at the poster. Please come. And the second thing we need to incorporate is basically symmetries in the sense that if you basically rephrase your polynomial in a different way, or you have an equivalent representation of your polynomial, you need to have exactly the same Q value associated to it. Okay, so these are the two things that you need to incorporate. So our main point of comparison of our approach is basically what we call the static approach, which is a very well-known method in combinatorial optimization, which basically consists in unrolling your inference rules for a fixed number of times. Okay, so what you do is that, let's say, for example, you want to prove that your polynomial P is non-negative. So you basically unroll your inference rules for one step, and then you try to search for a proof within this set of basically unrolling just one time. Obviously, in many cases, you wouldn't be able to prove that your polynomial P is non-negative in one step, so you need to go to the second level of the hierarchy. So L is this hierarchy. And then you basically search again, and so on and so forth, till basically you get that your polynomial P is non-negative. Obviously, this is exponential in terms of the size of the search space. So we show that we achieve, we show basically that the linear program is much smaller in our case to search for this proof. And please come to poster 120 for more details. Thank you.
All right, this concludes this session. Now there's a poster session in the East Exhibition Hall for 2 hours. Enjoy.